In this video, we're going to go over the sum and product rules of counting. So the general idea is this. If you've got some counting problem that you're trying to solve, so you're trying to count the total number of some occurrence or occurrences in a system you're dealing with, we can think about the entire system as shown here. Okay, this is the entire problem you're working on. Absolutely anything that could possibly come into play is contained within this system here. Okay, now within this system, you can have different events. Here's event 1, event 2, event 3, or maybe there's just one event. Okay, now with these events within your system, you're going to need to analyze and see whether or not any of these events are connected to each other. So is event 1 connected to event 2? Is event 2 connected to event 3? Or are events 1 and 3 connected? Or maybe none of them are connected. Okay, and the way it's going to work is, so you've got these different events, and you're going to count the total number of outcomes within event 1, and within event 2, and within event 3. So you'll have the total count within each event. Okay, and so from there to calculate the total number of outcomes within the entire system, if you determine that event 1 is connected to event 2, and by connected, you can think of this as when you describe the relationship between these two events, you'll be describing it with an and criteria. Event 1 and event 2 need to happen. Then to calculate the total number of outcomes for event 1 and event 2 connected, you're going to multiply the total number of event 1 outcomes by the total number of event 2 outcomes. That's the product rule. Because what the product rule says, the product rule is also known as the fundamental principle of counting. The product rule says that if you have one event that can occur in different ways, and you have another event that can occur in different ways, then the total number of ways that event 1 and event 2 can occur is n times m. Event 1 and event 2 can occur together n times m different ways. Okay, now, but if you determine that, let's say, okay, event 1 and event 2 are connected, and now let's say event 3 you determine with p different outcomes, event 3 is not connected to events 1 or 2. And by not connected, the idea is when you describe the relationship between event 3 and event 1 or event 2, you do this with an or criteria, an or statement, the total number of outcomes of event 1 and event 2 or event 3. Then to calculate the total number of outcomes, you add those different events. So if one event can occur n plus m different ways, if you kind of look at E1 and E2 as one event can occur n plus m different ways. And another event can occur p different ways, then the total number of ways that the first event or the second event can occur is this n plus m plus p. That's the sum rule. Now, at the moment, we're going to think about the sum and product rules from the perspective of there's no overlap between the outcomes of these different events. There aren't some outcomes of event 1 that are also outcomes of event 2 or event 3. Right now, we're just thinking about the sum and product rules from the perspective of all of these events have their own separate outcomes. We'll talk about how to deal with overlaps in the next video or the following video after the next. So for this system here, if event 1 and event 2 are connected, but then neither of these are connected to event 3, and the total number of outcomes of event 1 is n, the total number of outcomes of event 2 is m, and the total number of outcomes of event 3 is p, then the total number of outcomes in the entire system would be n plus m, or n times m, sorry. So in times m plus p. Okay, now one thing to keep in mind, though, is that event 1 or event 2 or event 3, in all of the upcoming videos, we're going to be working different example problems, where within each example problem, we might, to do the count, we might have to use different kinds of permutations, also the sum rule and the product rule, all within this one problem. And so to obtain n here from this event 1, this might be its own problem. This could be like any one of the problems that we're going to work in the upcoming videos, where we can, within this problem, we're using the sum rule and the product rule and permutations, etc. So just keep that in mind. You can look at event 1 or event 2 as its own system, where you do a full problem and you get a count, and there's your count, right? Like this count would come from any of the problems any example problems you work in counting, and there's your count. But within, to get this count, you had to use in its own right, the sum rule, the product rule, etc., etc. Okay, so to illustrate the sum and product rules, try and build your intuition for this, let's look at an example here. So first, let's count the number of different ways you can roll a 6 with a pair of dice, or pull a face card from a deck of 52 cards, 52 card deck. So the number of ways you can roll a pair of dice and get a 6, or pull a face card from a 52 card deck. Okay, and so when you're working example problems or you're looking at different tutorials, that's the way it's generally going to be asked. As far as if you need to use the sum or the product rule, it's going to be that or statement when it comes to the sum rule, and that and statement when it comes to the product rule. Okay, but to try and illustrate this more clearly, we can think about this from the perspective of if we were playing a game. Okay, the prize of this game is $1 million. If we win, we get $1 million. So how do we win? We win if we either roll a 6 or we pull a face card. So the game is, we're going to roll a pair of dice, and let's say we don't look at what the result is. Then we pull a card, and say we don't look what the card is. Then we step back. Okay, if we either rolled a 6 or we pulled a face card, we win the $1 million. And so the question is, what are the total number of ways we can win the $1 million? That's the idea of what is the total number of ways you can roll a 6 with a pair of dice or pull a face card. Okay, so when it comes to rolling a 6, we can think about, so here we have dice 1 and dice 2. Okay, so we could roll a 1 on dice 1 and a 5 on dice 2. We could roll a 2 on dice 1 and a 4 on dice 2. We could roll a 3 on dice 1 and a 3 on dice 2. A 4 on dice 1 and a 2 on dice 2. A 5 on dice 1 and a 1 on dice 2. Okay, so we've got 5 different ways to get a 6 here. All right, now when it comes to pulling a face card, there's 12 face cards within a 52 card deck. And so when we pull a card from this deck, there's 12 different ways we can pull a face card. We could pull any one of these, and that satisfies the criteria. So in that case, we've got 5 plus 12, so 17 different ways we can win the prize, win the $1 million. Okay, but let's notice how these are not connected. If we roll the dice and we get a 4 and a 2, 4 for dice 1, 2 for dice 2, then it doesn't matter what card we pulled. We've won the prize. We've satisfied the criteria. We rolled either a 6 or pulled a face card, right? If we roll an 8 and pull a queen of spades, well, then we've satisfied the criteria. We've won the prize. We rolled a 6 or pulled a face card. So there's 17 ways we can win the prize. There's 17 scenarios where we win the $1 million, where we either roll a 6 or pull a face card. Okay. Now, if these two events were connected, meaning the question is, how many different ways can we roll a 6 and pull a face card? So the game has changed. To win the $1 million, we're going to roll the dice. We're going to pull a card. We need to look at the dice roll and see a 6, but then we haven't won yet. We have to then look at the card and see it needs to be a face card as well. In that case, what are the total number of different outcomes that will result in a win? Well, it's 5 times 12. That's the product rule. If one event can occur M different ways, there's 5 different ways we can roll a 6, and another event can occur in different ways. There's 12 different ways we can pull a face card. Then the total number of ways that both events can occur at the same time is M times N different ways. Okay, 5 times 12 is 60. The different outcomes are, we could roll a 1 on dice 1, so we could kind of think about maybe this dice is marked 1, this dice is marked 2. Okay, we could roll a 1 on dice 1 and a 5 on dice 2. So there's one part of the criteria for us to win the money, but we're not done yet. As long as we have if we have a 1 on dice 1 and a 5 on dice 2, then if the card we picked is any one of these cards, we win. So we have to hold a 1 and a 5 and then just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Then, okay, we could also roll a 2 on dice 1, 4 on dice 2, and then get any one of the cards. Same thing with 3, 3, 4, 2, 5, 1. That's why you multiply. Those are the total number of different outcomes, and we'll win the $1 million. That's the total number of ways we could roll a 6 and pull a face card. Okay, now the last thing I want to note is, like we talked about in the previous video, don't confuse the general product rule, the fundamental kind of product rule, with permutations and combinations. Even though we do use the product rule for permutations and combinations, don't confuse something like this with thinking that, we're counting different arrangements. So no, we did not just count if we roll a 1 and a 5, 1 on dice 1, 5 on dice 2, and we pull a queen of hearts. Well, we're not counting, we rolled a 1 and a 5, pulled a queen of hearts, but we also pulled a queen of hearts and rolled a 1 and a 5. We're counting both scenarios. No, that's completely incorrect. This is not, this system here is not a permutation or combination problem. We have one event, the first event. There's 5 possible outcomes, all related to rolling dice. There's no way we could have, it makes no sense to say we rolled a 4 and a 2, and then we pulled a queen of hearts. Okay, so here's the second event. Well, it makes no sense to say that, okay, well, we're gonna count it with the other arrangement where we pulled a queen of hearts and then we rolled a 4 and a 2. There's no face cards over here. This is the 5 potential rolls of the dice. Face cards are over here. There's no arrangements here. The only reason permutations and combinations, that arrangements come into play, is because it's like if I'm saying, okay, what are the different ways that I could arrange these 12 face cards? All right, well, slot 1, slot 2, slot 3, slot 4, etc. Right? If I'm going to be arranging these, well, I can put any one of these cards in slot 1, etc. Well, okay, I can pick any one of the 12 cards here. Any one of these 12 cards. Then I'm left with 11 cards to pick from for this slot. Well, okay, I'm still picking from the same group. That's the big difference. When you're doing combinations and permutations, these different slots here are connected to each other. You're picking from the same group. This first slot could have been any one of the 12 cards. So if you actually picked a king of diamonds and then a jack of spades second, Well, that's fine, but you could have picked the Jack of Spades first and the King of Diamonds second. So you have to count the rearrangements. In general, though, just looking at the product and sum rules from the general perspective, you're multiplying this one event and this other event. You're pulling from different groups. There's 5 different roll the dice outcomes. There's 12 different face card pulling outcomes. So you can't have a face card over here. There's no flipping the arrangement. So keep that in mind.